We will now move to the presentation of François BAREILLE. So François will present us a paper co-author with Raja. So François is a research fellow in environmental economics at INRAE in the public economics, so also known EcoPub research unit. His research relates to both to environmental and agricultural economics, with special interest for land use, biodiversity, and climate change. So François, the floor is yours for around 30 minutes.
Okay, thanks Thierry. Thank you Raja for the invitation. I'm really glad to speak after Xiaomeng because the paper that I will present is really related to his work. It was quite an inspiration when we start and when we wrote the paper. So this paper is about the role of adjustments in the growing season also, but not in planting dates, rather in how farmers change their agrochemical input during the growing season to cope with fluctuating weather. And the idea here is to identify statically how these adjustments directly influence weather yields. So I will be quick on the motivation because we all know what climate change is a threat for agriculture. I will rather speak about how the literature has dealt with the assessment of the cost of climate change for agriculture. So we can see that there is like two big literatures. First one is simulation models with assumed behavior, like crop simulation models, as agronomists do, where you have a lot of information on the plant growth, and it's really nice because you can see how precipitation, weather interact on all the mechanism of the plant, and you have a nice theoretical relationship between climate change, weather variation, and crop yields. But you, as in these models, either you don't assume any reaction function by the farmers, or the assumption is based on like switching some practices, and it can be hard to see if whether or not these farmers really adapt in this way. You have all the Partial and general equilibrium models, where I will not extend on this because it's rather macro, while the other one are more micro, as we do here. The other literature is really more on econometric models, as Xiaomeng presented also, and it's based on observed behaviors, which is also nice because you can, in this case, nice about this literature is that you really see what farmers do, not what they will theoretically do in an optimal world, in optimal behavior. And so there's two types of big literature here: the Ricardian analysis based on the proposition of Mendelssohn and his co-authors, which is rather a long-term relationship where you estimate the price of land based on climate variables. And there have been a lot of concern here about the fact that the parameters are not well estimated enough. So there has been another literature, the panel approach, or what we call here the weather approach, where you capture short-term adaptation by the farmers. And you basically estimate the panel estimation of yields, revenue, profit function, or as Xiaomeng did, like directly the farmer's practice, as a function of the weather. So basically, this is what Xiaomeng presented. So you have in the weather approach, to be clear, we are inside this weather approach. We exploit year-to-year weather variation to estimate the impact of weather variation on year-to-year yields, revenue, or profits, usually using reduced form equation. So you have Z, which is either yields, revenue, or profits, and you have a set of weather variation, a set of weather variables, and you introduce fixed effects for year and fixed effects for the farmer or the region, and an error term. And what you estimate is the beta, and the beta is interpreted as the impact of weather on farmers' outcome, so either yields or profits. Once, this is really important, once farmers have undertaken adaptation. So it's not the direct impact of weather on crop yields, it's the weather impact of on crop yields once you have adaptation. And these parameters have been, as they have a lot of advantage in terms of precision and robustness compared to the former Ricardian analysis. So the weather approach, so yeah, it has solid advantage compared to the previous approaches, but actually there's limited effort to identify if really farmers do adapt or not. There is an implicit assumption that farmers do adapt, but if you regress yields or profits directly on weather, you do not verify if farmers adapt or if it's a direct shock on the yields or on the profits. So some studies have checked if whether or not these weather variables impact the adoption of specific practices, but it's rather outside the weather approach framework. And there has been 3 recent essays by Aragon, Jiangyani, and the paper presented by Zhao Meng, where they measure using the weather approach how farmers adjust during the growing season, either planting dates, for example. And they then compute how these adjustments, which are statistically measured based on observed behavior, how this adaptation impacts yields using back of the envelope computations. So it's not directly measured together, it's rather like it's another outcome. So it's not, it's bits different from the weather approach where you directly measure the impact of weather on yields. So the concern here is that does really beta capture the impact of adaptation? Say differently, if farmer do not adapt, the beta that you measure, it's basically the same that you will obtain in the crop simulation models. So it's very different to see if farmers do adapt or not, and if they do, how it impacts yields compared to the direct shock of weather. So here, the aim of the paper is to identify the impact of weather on crop yields and profits, while accounting explicitly for farmers' adaptation. And we measure here for adaptation as adjustments of input application, fertilizer and pesticides during the growing season. So how we measure, how we answer to our question. So we exploit weather variations together with input and price variations to identify and to capture and to assess the direct effects of crop yields through plant growth, as captured by former crop simulation models, where basically farmers do not adapt, and then the impact of farmers' adaptation on crop yields and farmers' expenditures. So we exploit these 2 types of information, weather variation and price variation, and we use them inside a structural econometric model where you have one yield equation for 3 crops. So we have a crop-specific system, and we have 3 crops. So we have 3 systems where we have one yield equation, one fertilizer demand equation, and one pesticide demand equation, and they will be all linked together by the structural parameters. This provides us, it allows us to identify the direct impact of weather on yields, the impact of weather on adaptation, and how this adaptation affects, as a result, crop yields. And we use a panel of farmers from La Meuse. So for those who don't know, La Meuse is a French department, so it's a rather small area, but it has the advantage to be really to capture for heterogeneity. So what we find here is that our structural estimates, so our estimates using our structural parameter model, are more precise than the usual reduced form estimate. This is already one contribution. But above all, we find that farmers do adapt in response to weather fluctuation. For example, if you take a RCP 4.5 scenario in 2050, we see that farmers should increase fertilizer application by about 3%, but to reduce pesticide application by about 7%. This allows us also, our estimates, to decompose the impact of weather on farmers' profit. And we can identify on one way the direct effect of weather on plant growth and the impact of farmers' adaptation on crop yields. So what we find is that adaptation always increases yields, but the effects are heterogeneous among crops. For example, we find limited evidence for weather, but strong evidence for barley and strong evidence for rapeseed, sorry. And we can finally conduct evaluation of the market and non-market cost of climate change. The market cost will be how climate change impacts the profit of the agricultural sector, and the non-market cost will be how climate change impacts the induced pollution by fertilizer and pesticide. And we see that actually farmers, the agricultural sector will lose about 3 million euros, but the remaining of society will benefit from adaptation, because largely due to the large reduction in pesticide application. So just a small conceptual framework. I will not enter into the details, but here our structural model is based on the assumption that farmers maximize their profit. And we assume that as we consider only the weather in the growing season, that farmers' single adaptation is to adapt variable input application, X. I, so I is the farmer I, J is the crop J, and T is the year T. And the program of the farmer is so to maximize this profit based on weather application, variable input application. It's a single control variable here. And they try to maximize the profit, which is defined as the price times the yield minus the price of the input times the input under the constraint of the production function, F. F is so depends only on X and W. So here, basic microeconomics leads you to the optimal input application, the theoretical input applications that you should apply to maximize the profit, given W. So afterwards, you can check how a change in weather affect profits. I will not enter at all into the details, but just to show you that you can theoretically identify the direct weather effect without farmers' adaptation. So X here remain fixed. So we have only a shock, a change in W that affects F, And you have here all what farmers do. Farmers change in reaction to W, to the weather. They change their variable input, which will affect the expenses, but will also affect the production function. So let me show you on a simple example what it means to distinguish the weather effects on crop yields. So assume you are in a theoretical, you are into normal weather, W, and you apply the optimal, the farmers apply X bar, in this case, X bar star, and you are in the point A, you have this production. Following year, you are not into the normal weather, you have a different weather, W1, and there is a direct shock. If farmers do not adapt, there is a direct shock here to arrive at point B, where you suffer from a shock of a weather shock. But farmers are smart. Farmers optimize, and what they will do is that they will adjust the variable input to maximize the profit. And here, without enough technical details, to have the optimal profit, you need to equalize here the derivatives. So farmers will put X, will increase X until they reach the point D, where in the point D they have the maximal profits they can have under this weather. So basically, you have a direct weather effect here, and the farmer's farmer's adaptation effect. And you can actually also disentangle this farmer's adaptation effect under two effects. The first one will be like a normal weather effect, normal adaptation effect. What is the properties of the production function under normal weather, and also the fact that weather impacts the productivity of X. So you see here the derivative, it's also equal to the marginal productivity of X. And you see that at this level, X, the variable input do not have the same marginal productivity. They have a higher marginal productivity under W1 for this level than under W bar. So basically, this whole story, we will be able to capture it in our econometric model. So let me check. Yeah, we try to speed up a bit. So all that I showed you before is it relies on a theoretical production function f, and we give it a simple form. It depends on three sets of parameters: the alpha, the beta, and the gamma. And it has easy agronomic interpretation. You can think of the alpha as the maximum yield of crop J that you can attain. For example, for wheat, let's say it's 100 kilogram per hectare. It's the maximum yield you can reach into the best condition. And to reach this level, you need to put the X until beta. So beta is the required input that you need to apply to reach alpha. And gamma here is the marginal productivity of the variable input. So here it's a simple model. What is new here is that we say that the alpha, the beta, and the gamma depends on the weather variables. So basically, we decompose the set of parameters at 5 parameters each time. A parameter that is independent of weather, alpha 0, for example, and 4 parameters that depends on weather, on growing derby days, growing derby days square, growing total precipitation, and growing total precipitation squared. So this is a production function, and in our conceptual framework, we have the optimal X and the optimal Y. So you can derive here, you can find what are the optimal application of X under W. So it provides us a system. Sorry for, I will not enter into the details neither, but you see that you have still the alpha and the beta here. And then you have a delta. The delta is actually a combination of the gamma before, so of the marginal productivity. So delta is a parameter of productivity. And you see here that it depends also on prices, on the price of the X, so of the input, and the price of the Y, the price of the crop. And here, so you have for one crop J, you have this equation Y and 2 equation X, one for input K equal 1, fertilizer, and one for K equal 2, pesticide. What is nice here is that you see that the delta are shared among the equation. So it means that it's theoretically consistent that you apply X in order to modify your crop yields in order to maximize your profit. So here we will see directly that when you change X, it will be due to the productivity of the input. And this system allows you to recover the optimal profit, the higher profit you can reach. So, and as in the weather approach, we add crop, so individual fixed effect and time fixed effect, and the remaining error term here. And so we estimate our structural model using a seemingly unrelated regression. that allows us to correct for the correlation between the two error terms. So where do we estimate that? So we estimate this in La Meuse, and we obtain why we are in La Meuse. It's because we have a really detailed, really rich database where when you know basically the crop, you know the crop profit per hectare, but you know also the crop yield per hectare, and above all, you know how the fertilizer and pesticide application per hectare for each crop. So we know how farmers have used the different pesticides under the different crop. So we don't need to make assumption on how farmers allocate their pesticides and fertilizer. We directly observe them. And so we exploit this information together with weather variables from Meteo France. So what are our estimations? So here is the estimate. And the estimates, it's really hard to understand them. Even me, I have to really focus to understand them. But what is cool is that you can reuse the alpha, the beta, and the delta that you have estimated to recompute the direction function, so the crop yield, theoretical crop yield, given these estimates, and the variable application of fertilizer and pesticides under weather. So this is what we show here. What we see here for wheat. So here you see the evolution of wheat profits. So the black line for the different growing degree days in La Meuse over the whole period. The blue line is the yield response along the growing degree days. The green line is the application of fertilizer, and the red line, sorry, the green line is the application of pesticide, and the red line is the application of fertilizer. And we see, given our estimates that we have computed, we can recompute all these curves, and we see that when it's, for example, when it's hotter, you see that the yield decrease. And that farmers replace pesticide by fertilizer. You can compute the same stuff here for precipitation. We see that the replacement of fertilizer and pesticide is less convincing here. So farmers tend to less adapt to change in growing total precipitation. But we see that there is still a change in profit and yields, actually likely here because it's a direct effect of weather on crop yields. So you can do it for barley also, and for rapeseed. So if I check for barley, for example, we see that you have less a curve. It's really directly, you see that when it's the temperature increase, you have a straight reduction in barley yields. And even if farmers adapt a bit, the impact on profits is also negative. For precipitation, it's flatter. And if you look at rapeseed, which is the most valuable crop here, you see less adaptation here. Actually, farmers tend to increase pesticide and to maintain fertilizer, but you see that it's consistent above the three crop, that you have a reduction in yields when there is hotter temperature, and reduction in profits, which is also in line with all the literature. So if we are, as we focus on adaptation here, here is a graph of the focus on how farmers adjust their fertilizer application, the red line, and how they adapt their pesticide application, the green line. When you aggregate for the three crop, and you see a clear line that when there is hotter temperatures, farmers reduce pesticide, and that there is a curve, a U shape on fertilizer, and you have the opposite for GDP for precipitation. So we can, because one of our objectives here is also methodological. You can compare our structural estimate. So here is the elasticity. So the elasticity, for those who are not familiar with, it has to be interpreted as how, for this case, how a change of 1% in GDD affect, in terms of percentage, the profit of the crop. So for example, if you look at rapeseed, when you increase by 1% GDD, you reduce by 1.23% the rapeseed profit. And you have all this, at the central point, you have all these estimates in our case. And in the case of reduced form estimation, you have only, so basically you have only it for profit and yield. And you see that overall they are less, even if they are comparable, they are less precise in the reduced form estimation, especially for temperatures, where we see that in our case we are always more precise. It's less true for precipitation. So then you can simulate the impact of climate change using our response function here. It's really easy because here is a central point and you will see the new climate change, for example, an increase. So you just have to take the response here. So it's really easy to simulate climate change in our case. So we take a RCP 4.5 scenario in 2050 using the projection of the model of Météo France. And we see that temperature will increase on average by 1 degree, so which represents more or less an increase of GDD by 8% for wheat barley in one case here and rapeseed here. And that precipitation will also increase to about 26% compared to our period. And so we use the expected response of our structural estimate to project the future profit, yields, and variable input application. It's, as I showed you, it's ready to take, in our case of rapeseed, here was the previous estimate, and you just take the green line, the red line, and you display the corresponding change. So here is the detail. So we did it for only growing degree days, so temperature, or only precipitation, but I will focus here more on the total. So you see that basically you have a small increase in wheat, but it's not significant. A small decrease in rapeseed profit, but it's not significant neither. And a large decrease in barley profit, which is significant. So barley profits will reduce by about 14%. And you can see why it's like that. You can see, for example, that the yield of barley will reduce by about 11%, and that farmers will increase their fertilizer application by 5%, but reduce their pesticide application by 11%. In this case, it's not statistically significant compared to the initial level, but it is significant for wheat and rapeseed. So you can play with these estimates. I do not enter into the details. What I want to spend more time with you is on the decomposition of climate change impacts on yields. So here there are the change in yields from the previous table. So we just here 0.63%. It means an increase of 0.63%, and it only corresponds to an increase of 44 kilograms per hectare. And you can decompose this figure that we showed before into the direct effect of climate change, so without farmers' adaptation, so the direct shock, the real shock, and how farmers adapt. So what is the consequence of their adjustments in fertilizer and pesticide application on yields. So you see that we have issues to identify them properly, but the central points are always positive. and that they can reduce quite a lot the shock. If you look at rapeseed, for example, you have a shock that if farmers did not adapt, they will reduce in the future climate change, they will lose about 272 kilograms per hectare, but they adjust their variable input application to increase, and they increase it, they increase the yield. It leads to an increase of yield of about 200 kilos. So the net effect is rather small compared to the initial shock. So for rapeseed, it's clear, you have a beneficial impact of adaptation. For barley, actually, you have a much less beneficial effect of farmers' adaptation, even if it's in terms of it's only in absolute term half of the impact on rapeseed, because you have a very big shock of the direct effect. The total impact is still very huge. So actually, you reduce only by 15% the direct impact. And for wheat, basically, you have nothing. It's like small in amplitudes or in commented. So this is really we saw it as one of our main contributions in the paper. But what we can do also is to then estimate, to go a bit further than what people usually do. Usually people, they identify the cost of climate change looking only at the market impact. So how the profits, how the agricultural added value decrease under future climate change. But here we know that it will also correspond to a change in fertilizer and pesticide application. So we use in the literature the social cost of pesticide. So basically it means here that if I look at pesticide, that 1 kilogram of pesticides costs for society in terms of pollution's health impact between 100 and 400 euro per kilogram. And for fertilizer, it's much less, but actually farmers use much more fertilizer than pesticides. So the two costs are about equivalent. And so what we take here is a central value, so 250 for pesticide and about 3.5 for fertilizer euro per kilogram. And we use the initial the quantity that they applied in our panel, and we assume that the technology remains constant, the growing area remains constant, everything remains constant, the price also, and we value this non-market impact of farmers' adaptation, and we see that in total, you can do it by crop, for temperature only, for precipitation only. But you see that in total, here you have an increase, which is not significant also, but a central estimate of about 6 million euros in terms of additional benefits that farmers' adaptation provide to society. And you see here the reduction in terms of added value for agriculture, so some of the profit of about minus 3 million euros. So you see basically that the non-market impacts are greater than the costs of climate change. So we do not say it's the good value, but it provides new insight on the fact that maybe climate change is not that costly if you not take into account only the market cost, but also the non-market cost of agriculture, of climate change on agriculture. So I think it's time for me to conclude. So most of the studies that quantify the cost of climate change on agriculture use reduced form equation, where they basically assume that farmers adapt here and they measure the cost of climate change with this crucial assumption. But they do not verify that farmers do adapt. So in this case, it's hard for me to believe that economists should be more trusted than agronomists to answer to the cost of climate change if farmers do not adapt. So here we try to see if farmers adapt. And we propose a structural system where we can distinguish the effect of weather and profit through the direct effect on plant growth and the farmer's total adaptation that we can decompose. And to identify them, we use both weather variation and price variation. This, I didn't say it, but the fact that we introduce price variation is why we can identify all of this. And we can compute if farmers adapt and how it translates to crop yields and crop profits. So these are the takeaway messages. I explained them during the presentation. So we show that our structural estimates are more precise than the previous estimates. And above all, we show that there is adaptation from farmer side. And we see that in the case of RCP 4.5 scenario in 2050, farmers will increase fertilizer by about 3%, but reduce pesticide by about 7%. And that this adaptation, the fact that you replace pesticide by fertilizer, it allows you to increase the yields under future climate conditions. And that actually climate change, when you introduce this adaptation and the pollution they induced, you see that climate change and the adaptation of farmers could actually benefit to society. That's all for today, and thanks you for listening.
Okay, thank you very much, François, for your presentation. We have now some time for the question. So don't hesitate to put your question in the discussion or to raise hand if you want to ask some question. We already have two questions in the discussion. The first question by David. So David asks, why do you use fixed effects rather than random effects? Do you see the question in the discussion, François?
Yeah, okay. Yeah, I'm trying to catch up. So yes, that's true. But here we have our sample represents 1/3 of the total agricultural area in La Meuse. So we consider that it has an external validity, that we have a representative sample of farmer. And so the assumption for climate change simulation, it's only that you assume that the 2 other thirds are equivalent to the third that we have in our sample. So it should not be a big assumption. Mm-hmm. And above all, if you do not use the fixed effect, you cannot identify properly the weather shock. You have difficulties to properly measure, to remove all the what we call the omitted variable biases, and it could affect the estimation of the alpha, beta, and delta. So, and it's a discussion that we could also have with Xiaomeng. The fixed effect here, they allow you to really remove all this noise and to really focus on the shock, the weather shock, and in our case, the price shock. And then to extrapolate our result to the remaining of La Meuse, for us, it was not a big assumption, but probably we should really check if it or 1/3 of the agricultural area is representative of the other one. And we should be able to do it.
Okay, thank you. So we have another question from Stefan. In fact, Stefan raised a question that I also add about the area allocation. Does the area allocation change in the simulation, or is it something else?
So the question of Stefan, I thought it was also in the structural model. So I will answer to both. So in the structural model, if you want to identify the impact of weather shock on crop allocation, to measure it statistically, you have to make assumptions on how farmers anticipate the weather in the growing season. In La Meuse, they basically decide their crop allocation in November, December, and the growing season starts 1st of March and ends the 31 of August. So you have to make an assumption on how they anticipate this, because otherwise, with the fixed effect we introduce, you have no variation. For example, if you assume that farmers anticipate normal weather condition, with a fixed effect, you have no variation. So you cannot identify this. But it's a good point, because we are thinking on, as an extension of the paper, on how to model the anticipation of farmers, because there are more and more papers on that nowadays, to try to identify how farmers also adjust their crop allocation in the short term in response to weather shock, to anticipated weather shock. So for Thierry, for the simulation, what we could do actually would be to correct for the fact that, for example, wheat will become slightly more beneficial, and barley will be, the profitability will reduce a lot. So we should, or we could, take it into account for this point by assuming that farmers will replace barley by wheat or barley by rapeseed. But we did not, because there is some kind of assumption to do there too. You have to either we pick some elasticities of substitution from the literature to understand how farmers usually change their crop allocation, and it's available, but we did not want to make this kind of back of the envelope computation, but and because also the extension would be to really catch this crop allocation change. And so in the future paper, hopefully we could understand how farmers will also switch the crop allocation and how it will reduce the cost of climate change for farming.
Okay, thank you very much. So I think we have also a question by Stéphane.
In the paper, we use more precaution, but yeah, it's heavily dependent on the social cost you take. But even if you take the minimal part, you have still some positive effects. So it does not, maybe it does not compensate totally, but it's easy to take into account. And for surprise by hotter temperature, it's more pesticide use. I didn't explain it, but it's just that pesticides are less productive in future climate change, in future climate, and fertilizers are more productive. So that's why you have a substitution between the two. I will thank you, Thierry, and everyone for your comments. Really enjoy the discussion and the presentation. Thank you, everyone.